voltage. Motor is spinning up. Rotational speed has stabilized. Hello friends, and welcome to another episode of The Post-Apocalyptic Inventor. In this episode we're going to talk about an electric motor test stand, or dynamometer, in short Dyno. The parts of which I have collected over the course of about 1 year, and we're going to take a look at all those parts. And, well, then I'm going to tell you what this can be used for, and we'll make some actual test runs with different motors. And later on then I'll explain how it all works, and, well, tell you what needed to be done in order to get this all running again, because there was a whole lot of reverse engineering, repairing, and modifying involved. So what was a setup like this originally intended for, and what can we use it for today? This equipment here was built in the 1970s by a German company called LW, and for many thousands of US dollar equivalent, this was sold to a school or university where the students would then experiment with this and learn the electrical and mechanical behavior of the different motor types, some of which operate on completely different physical principles. Since those days, technology has advanced, of course, but I see no problem in just connecting a brushless DC motor, stepper motor, or modern industrial servo motor to this brake just as well as you could do it with the old motors. It also is very easy to add a digital data logger to this device by just connecting a cheap Arduino. And I'm intending to use this test stand in order to make tutorial videos about the different motor types, and I will then be able to show you in practice how the different motors behave, and you will get to see something that you would otherwise only see if you were to visit a certain school or even university. But what would be a practical problem right now that this test stand could help us with? Well, imagine you have salvaged an unknown motor, like this capacitor motor here from a dishwasher. Or maybe you have bought some motor for just a few bucks online, but you know nothing about it. Without a test setup like this, you would have a hard time finding out what operating conditions the motor was actually designed for. But what are those operating conditions or characteristics of the motor that you should know about? Well, let's just pick an example here. If you buy an electric motor as a new part, you often can get a data sheet that will give you the most important data or even characteristic curves of that motor, and let's just pick an example. This DC motor here, for example, that I bought recently. We'll take a look at this right now only very briefly, but I'll explain all of it in detail later in this video. The most important data points that you want to have are: how fast is the motor going to spin at the rated supply voltage when no torque is applied? At which torque is the motor going to stall? How high is the current under no load and at stall? Where is the point of maximum mechanical power output? And where is the point of highest overall efficiency? And guess what? While you might get this for a motor that you bought as a new part somewhere, I can now get this for any motor that I managed to connect to my setup here. But guess what? Before we go into all the details and explanations in theory, let's have a little fun and just take a look at what I have collected here, what kinds of motors are part of this set here, and then we'll just have a few actual test runs. Series wound DC motor, aka universal motor, shunt wound DC motor, and compound wound DC motor. Shaded pole induction motor with motor capacitor, aka capacitor motor, normal 3-phase induction motor, and here, really the odd one out, slip ring motor. The first of the smaller magnetic powder brakes, here coupled with a piece of rubber to a second DC compound wound motor. 3 identical combined power supply control and measurement units that can measure, control and regulate the speed and torque applied by the brakes. A massive industrial scale magnetic particle brake, and 3 massive 3-phase dummy loads consisting of wire-wound rheostats. And last but not least, a rather large educational style cosine phi or power factor meter that is required when the real and not just the apparent input power of a motor that is powered by alternating current, is to be measured, for example, in order to find the point of actual highest efficiency. And right now, let me give you a very brief and basic explanation of how all of this works together, while I'll give you a much more detailed breakdown and explanation of the circuits and all the technology involved in a second video, because how it works internally is really a completely different question from how it's used to measure motors, what we're going to do now. First of all, I can use my adjustable isolation transformer and or my DC lab power supply in order to supply the motors with variable voltages. As I've shown you a minute ago, the motors are then coupled via a piece of rubber to one of the magnetic powder brakes. And within that piece of rubber, there are 6 small magnets that pass by a Hall sensor. So you get 6 pulses for each completed revolution. The magnetic powder brakes work by basically magnetizing magnetic powder that is in a cavity between 2 parts that rotate against each other. When the magnetic powder is magnetized, magnetic bridges are formed, which then create a friction between the 2 parts. And within a certain operating range, a current can be fed into the, coil inside that brake, and then a more or less proportional torque can be applied to, for example, a motor. And one of the great things about this technology is that these brakes can be controlled with very little control current, but they can apply a lot of torque. And on the bottom side of these brakes, integrated in a small enclosure, you can find an arrangement of strain gauges. A strain gauge bridge, in German Dehnungsmessstreifenbrücke, is used in order to measure the exact torque applied to the motor shaft. And the control units do not only supply the brakes, but they can also regulate them so that either the rotational speed or the torque is kept more or less constant. In addition, these control units also give out a pulse signal that can be used in conjunction, for example, with a simple Arduino that acts as a data logger so that we can digitally read out the rotational speed. But we can also grab an analog value from these devices that is proportional to the measured torque. So via an ADC, this can also easily be converted into a digital signal. My Arduino setup here was really just put together very quickly within one afternoon, so the code here is, temporary at best, so you better don't take that as a good example for doing this, but it's good enough to plot the motor speed while I manually dial in different torques. And that is how I can at least approximate characteristic curves that we'll take a look at in a minute, and we can then, for example, derive the point of highest output power or efficiency. So, first experimental setup. What is going to happen now is that I will step up the supply voltage from 0 to 230 volts AC, and you can read that value off here on this multimeter. And the brake will be disengaged at first so that the mechanical load on the motor will be at a minimum. But you can read off the rotational speed, and you have to multiply the number by 2000 here because the scale is set to 6000 revolutions per minute max. After that, I will then engage the brake, go into OR, ohne Regelung, I guess, without regulation, and that means that we will apply a constant torque, not a constant speed. And then we will go into MR, which I think means mit Regelung, with regulation, and then this control unit here will try to stabilize the rotational speed of the motor. So let's see what happens. Turning on isolation transformer, cranking up to get enough start torque. You can see motor is spinning up, 2000 revolutions per minute. 3,000 revolutions per minute and climbing, going on 4,000. And this is the typical behavior of the universal motor or, series wound DC motor. It will not easily stabilize at a rotational speed, but rather climb and even run away when you crank up all the way to the rated voltage. Now engaging the brake and stepping up the braking torque. So I've applied around 0.25 Newton meters, and you can see the speed going down, but not really being stabilized. Now MR with regulation. You can see this is swinging in, and now it has stabilized at 3,000 RPMs. And now I can just set a speed. For example, 2,000, or actually, 4,000. Going back to 3,000. Turning it down to 2,000. And you can see that the torque is now at 0.35 Newton meters. And we can already hear that we are approaching the stalling torque. And we can also find that. Let's go down. We go to without regulation, and the motor has stalled at around 0.45 Newton meters. Turning off supply voltage. Engaging input voltage. Motor is spinning up. Rotational speed has stabilized. Apparent input current 2.5 amps at a cosine phi of around 0.4 to 0.45. That means that half or less than half of the input current, of the apparent input current here, is actually a real current. So we're talking at an input current right now of 1.25 amps times 230 volts. Now let's engage the brake and apply some torque. Stepping the torque up. 0.1 Newton meters of torque. 0.15. 0.2. 0.25. 0.3, 0.35, 0.4, 0.45, 0.45, 0.4, 0.5, 0.5, 0.55, approaching 0.6, 0.612, 0.63, 0.65. Motor is slowing down. 0.66, 0.67, 0.68, and stall is reached. 3.8 amps, 0.6. Next test setup. The shunt-wound DC motor is sitting on the test stand. Via a bridge rectifier, it is connected to the isolation transformer. So we'll supply it with a pulsating direct current, not with an alternating current. The voltage across the motor can be read off of this display here. And let's just slowly increase the supply voltage and then take a look at the speed the scale is set to 3000 revolutions per minute. Now I'm just setting this to a value of around 100 volts. And you can see that unlike the series wound DC motor, the rotational speed is just stable. And again, I go up to, let's say, 150 volts. And again, we have a stable rotational speed, in this case, somewhere over 1000 revolutions per minute. And I'm cranking this up to around 200 volts. I'm not going any higher because I don't know what this motor is rated for. But here we are, somewhere around 1400 RPM, and the motor is not speeding up like with the universal motor. Now let us apply some torque. Going up to 1.0 Newton meters, and you can see a slight drop in the rotational speed, but nothing too wild. Same at 2.2, 2.3, 2.35, 2.4. It's now at 1200 revolutions per minute. 2.45, 2.5, 2.55, 2.6, 2.65, 2.7, 7.5, 2.8, 2.85, 2.9, 9.5, 1 Newton meter. So we can already tell that this motor is obviously rated for a higher torque. You can see that the voltage has dropped. That's because of the internal resistance of the power supply. So I will go up again. Would be better to have a regulated supply. Now I'm setting the torque scale to ×2, and I'm going up again. So we're at 1, 1.1, 1.2, 1.4, 1.6, 1.8, all the way up to 2 Newton meters at 1200 revolutions per minute. And that's the maximum that I can do with this setup. So I'm sure that that was probably a lot of information to take in for some of you. But that's also kind of the point here. I wanted to show you that even though I just picked 3 of the motors, we have already seen very different behavior and lots of different quantities that were measured and that were variable. It's not as easy as just buying a 12 volt 110 watt motor. It really works differently or behaves differently in every operating point. And some of the things that we saw and that we can keep in mind, for example, is a series wound DC motor or universal motor is really only break down by friction or by air resistance or by load connected to the motor. Otherwise, when no load is applied, it basically doesn't have a stable rotational speed. The shunt-wound DC motor, for example, where the field coil is not connected in series but in parallel and where the motor is then supplied with direct current, has a very stable rotational speed, even though it's quite similar actually. In this case, a motor of a similar size also was built for much lower speed and much higher torque apparently. The shaded pole induction motor, which is physically very different from the 2 DC motors, again had another characteristic. It first needed some time to spin up, it didn't have a lot of starting torque, but then it stabilized at a rotational frequency, and even though I continuously increased the braking torque, the speed of the motor only went down slightly to then abruptly stall. Also, we haven't really done the calculations yet. We could also clearly see that it is absolutely necessary to measure the power factor or cosine phi in order to determine the real input power of an AC motor, especially if it has a cosine phi of 0.5 or less, because The normal current that we're measuring with a multimeter is really misleading because the power that it seems to draw is twice what it really draws. But even if you correct for the power factor, the shaded pole induction motor is still taking in way much more power than it puts out, which means that it has a terrible efficiency. So I'm not sure if this really helped to clear things up or if it just added to the confusion. But maybe it helps if we still take a look at one of the data sheets from one of those motors I bought, because there are the data that we want to get. And if you watch this 2 times maybe, you will see that a lot of the data that are in that data sheet could be taken from the experiments that I have just shown you. So here is the data sheet supplied by the Johnson Electric Company, and it contains various curves and numbers. Let me modify and simplify this a little bit, and then we'll go through it step by step. Now, our first curve here is the rotational speed of the motor as a function of the torque applied to it. The x-axis shows the torque from 0 to 700 millinewton meters, that's 0.7 newton meters, and the scale for the rotational speed goes from 0 to 8,000 minute to the -1. That means the same as RPM, only that it's mathematically correct and can be used in calculations. Now we have a point of no load, that is where m is 0, the torque is 0, and the motor will then spin at a rotational speed of 7,000 revolutions per minute. If we then ramp up the torque all the way to somewhere between 600 and 700 millinewton meters, the motor will stall, it will stop rotating, so N will be 0, but torque will be max, and that is called the stall torque. Our second line shows the input current as a function of the torque, and that goes from somewhere at around 1 amp when the motor is spinning under no load at 7,000 revolutions per minute, all the way up to the stall torque where the current becomes maximum and is between 35 and 40 amps. Our third curve shows the output power, the mechanical output power, not the electric input power, as a function of the torque. And you can see that it is maximum at a torque of around 1/2 stall torque, and that is very typical for permanent magnet DC motors. And that means that this torque is the operating point of maximum power output, and if you increase or decrease it, you will always decrease the mechanical output power of the motor. And our fourth curve here shows the overall efficiency of the motor, and that is defined as the mechanical output power divided by the electrical input power. And the operating point of maximum efficiency is at around 75%. That means that only 25% of the electrical input power will be lost as heat, while around 75% are converted from electrical power to mechanical power. But you can also see that that point of maximum efficiency is much more in the first third of the allowed torque range here, and quite far away from that point of maximum power. And now let's go to the actual numbers and see how we can derive them. You simply draw a line at the torque value that you have chosen here, that's at around 1/2 stall torque at the point of maximum power. And now you can draw lines to the various scales. Here we can read off the maximum output power of around 116 watts. Here the intersection between rotational speed and torque gives us the momentary rotational speed of around 3,500 revolutions per minute, a current of around 18 amps, and an efficiency of only around 52%. So in other words, when this motor is operated at maximum output power, half of the electric input power is sadly converted into heat, not into mechanical output power. However, on the other side, if you were to choose the operating point of maximum efficiency, you were at around 75% efficiency, but the power that you're putting out is only at around 60 watts, so only about half of what you can do at maximum. So I hope you found this interesting. Maybe you learned 1 or 2 things, maybe you even found this entertaining, who knows. As you can probably tell, I would like to tell you more about this stuff, how it works internally, how I repaired it, but then of course in the long term make videos about the different kinds of motors where this test stand will be just, well, one means of explaining how they work and how they can be controlled. But no matter what, I hope to see all of you soon, and if you want to get regular smaller updates about my channel, then you should probably visit my Facebook or Patreon, where you can of course also support my channel.